So, we're now ready for the final talk before the panel session, and we're very happy to have Cynthia Dwork here, who will be starting in Harvard come January, but is of course known for her previous work at Microsoft, and is a recipient of the Dijkstra Prize for her contributions, and especially she is well known for her contributions to making differential privacy stand on a firm mathematical footing. So we're very pleased to have her talk about theory for society and fairness in classification. And if you can't hear me, don't worry, Cynthia is wearing a microphone.
Okay. Well, it's still a pleasure to be here. It was a pleasure to be here when I spoke last week, and it's still true. I'm not going to talk about privacy. And for those of you who are just starting out in your careers, I'm arguing in favor of theoretical computer science. So differential privacy came from theoretical computer science, and the work that I'm going to talk about next is also squarely in that discipline. And I'm particularly interested in finding applications of theoretical computer science that can have an impact on societal issues. So that was what we tried for with privacy, and now we're embarking on another effort along those lines. So there is a role for theory in this world. Systems are being built and promises are being made. Your privacy is important to us. You know, what are they talking about? The translation from spoken language to mathematically rigorous guarantees happens in the algorithm. So when you're designing an algorithm and when you're programming it up, what are the consequences of what you're designing to the values of interest? What is the boundary between what can be achieved and what can't be achieved? Differential privacy in some sense arose from negative results, from showing that certain things that you wanted to do aren't really doable. Those boundaries played an incredibly important role in the field. What guarantees are actually feasible? Now, you all probably know just from reading the popular press that algorithms can be biased. Here's an interesting example because I've heard Al Roth speak about this example. He was involved in it, and yet the motivation that he gives when he speaks about it now isn't the same as the one that you find if you read the paper. So just for fun, the National Resident Matching Program matches graduating medical students, who are called the applicants, with hospital residency programs. So let's call them the applicants and the programs. So the applicants rank all of the programs, and the programs rank all of the applicants, and some kind of stable marriage algorithm is then run. Now, originally, the algorithm that was run was program proposing. You can make the algorithm either program proposing or applicant proposing. They made it program proposing. And this was changed in 1997 in response to a crisis of confidence concerning whether the matching algorithm was unreasonably favorable to employers at the expense of applicants. Now, there's no secret hidden bias here. Everybody knows, I mean, everybody who has studied the math of the stable marriage problem knows that the proposers have an advantage. It's proposer optimal, and it's sort of being proposed to pessimal. And somebody made a choice, oh gee, who's running the program? Somebody made a choice as to who was going to get the benefit. It wasn't a secret, it was just a policy. And it was reevaluated and changed. And another thing that happened during this changing was that the algorithm was played with a bit in order to be more fair to married couples. And that is the point that is emphasized in the more recent lectures. You've also probably heard, though, of classifiers being inherently biased because they are trained on data, because when you learn a classifier using machine learning algorithms, you're training it on data. And the data has historical biases built in. They are the historical records, and previous methods were biased, so you're teaching that bias. Okay. And I just want to comment that when you think about these things deeply, the consequences of the bias are less obvious than you might think. And we'll return to this particular point later. So Richard Burke is an expert in using statistical methods for predicting outcomes in with prisoners who are going to now be released. So it's apparently, I haven't read the whole literature, but apparently algorithms do much, much better than humans. So it is useful to use these, and he argues for them. But he makes this point, because a lot of times there's a discussion about the role of race in the bias, in the algorithm. The central question addressed is what role race should play as a predictor when, as an empirical matter, the majority of perpetrators and victims are young African American males. So he's talking about predictors that predict what is the chance that somebody who is coming out of jail is going to be involved in a murder, either as perpetrator or as victim. And he emphasizes that these killings are intraracial. So this just gives you an idea of the kinds of ethical and philosophical issues that you have to think about when you play with these things, when you tinker with them. Now, my interest in this started in about the summer of 2010, when I was simply looking for some new problem to work on that wasn't differential privacy. And this eventually resulted in a paper with Harsh Patassi, Reingold, and Zemmel. And the concern for our version of the problem was you have a population, and it includes minorities of various kinds, and you want to be sure that the algorithms that you build don't discriminate against your minority groups. And for the purposes of this talk, we just are going to have a single minority set, which I will call S. And the rest of the population is sometimes called T, and it's sometimes called S complement. So about the time, this was in August, and we started our work in May or June. The Wall Street Journal published in its series called, I think, What They Know, it talked about a problem very similar to the one that we were looking at. So they described a real-life situation where there was a bank, Capital One, and when a user would navigate to CapitalOne.com, before being shown anything at all, Capital One checked with a tracking network, X+1, to learn demographic information about this person, this user. And X+1 had placed individuals into some, tens of bins with suggestive names like white picket fences. Based on what bin you'd been placed in, you got a different online experience. And the concern that was raised in the article, and to my best recollection, they were not actually accusing CapitalOne.com of this. They were saying that this was a potential concern, is the possibility for the illegal practice of what is called steering, which means steering minorities into credit card offerings of less desirable terms, higher interest rates. This example also lets us set up a framework that we were looking at. Remember, this was work that was done at Microsoft. Microsoft has an ad platform. So we have a bunch of individuals. Our set of individuals is called V, and a given individual is typically X or Y. And there's a ton of information about these individuals. This is everything that the tracking network knows about you. Then there's a mapping that takes individuals and places them into classification outcomes. those are those bins that I mentioned, the white picket fences. So an individual X gets mapped to M times X, MX. This is the interface that is exposed to the advertisers. And the advertiser then takes sees what somebody's bin is and acts accordingly by applying some function F. That could be choosing which ad to show them, or whether to advertise or not, or how much to bid on the ad, and so on. Arbitrary actions. So the vendor is the person who's doing the advertising. So A is our set of vendor actions. Okay, so that's the general setting that we're interested in. And when you want to talk about discrimination, the first thing that people say is, well, make sure that the algorithm never uses the information about whether or not somebody is a member of the minority group S. So make the algorithm S blind. And you probably all know that membership in S can be holographically embedded into all of your other attributes. And just checking that an algorithm doesn't explicitly check for S tells you absolutely nothing. And here was a really nice example. This was simply a project in a course that was taught at MIT. The students were Jernigan and Mistry. And what they showed was if you were gay, male, then a lot of your friends were self-declared gay men. So just by seeing how somebody's friends described themselves, you could identify who were the gay males to a large extent. Okay. So I've done a lot of work in cryptography, and when you build a cryptographic primitive, you have to say, what are you trying to accomplish, and what bad behaviors are you trying to rule out? So for example, if you're looking at an encryption scheme, an obvious bad behavior is that an eavesdropper who sees the ciphertext shouldn't know what you're saying, but you have to formalize that well. There are other things that you will want, but that's one of them. So we simply sat down and we wrote a catalog of evils. We made no claim that this was an exhaustive catalog, but we just wrote down, these are things we'd like a system to rule out. If we have a system that rules this out, and then somebody realizes that there is something else that ought to be ruled out, fine, build another system, science advances, and it's a path of progress. But we wanted to rule out certain things. And we came up with some obvious things to rule out. Some of you have heard of redlining or weblining. Redlining is the practice of basically discriminating based on zip code in the United States, for example, in determining whether someone's eligible for a loan. But of course, zip code is a proxy for race. So we came up with some obvious ones, we came up with some non-obvious ones. This is a short talk, so I can't go into those, but I'm happy to try to tell you about them separately. You might want to capture social constraints, like in the Indian parliament, a third of the parliamentarians have to be female. You might want to say a third of the applicants that are admitted have to be female, or something like that. Also, we wanted to provide a sort of normative approach to preventing discrimination, specifically in an ad network system, but sort of more generally. But in the ad network system, an advertiser who was using the system would not have to concern itself with regulatory issues, because they would know that they were not discriminating because the system prevented discrimination. So we want to be able to do this without, say, explicitly finding all of the redundant encodings and so on. And we also wanted to retain flexibility for, now think about the advertising online setting. You have arbitrary, unknown, potentially malicious, completely hard to get your hands on and audit vendors. On the other hand, they may be totally legitimate, and we'd like them to be able to choose which segment of the market they're going to target their ads at, and so on. Okay. We want to be able to do this, obviously, without knowing them or understanding these people, because you never get them and you don't have any time. The ads have to come out faster than I could snap my fingers. Now, there are a couple of words I could say about flexibility for the untrusted vendor. I'm going to be really fast here because it's a short talk, but the main point is that, first of all, if we were intuitively, and this can be made rigorous, if we're fair in our mapping from individuals to classification outcomes, then, since the vendor only sees the classification outcome and nothing else about an individual, we retain fairness under post-processing. So that means that the vendor's actions can be arbitrary and actually, in terms of fairness, don't enter into the picture at all. And we can focus on the classification step, ignoring what the vendor is doing. And that sort of exposes the core problem. And it turns out you can incorporate vendor preferences in the classification step. It's delicate, and you'll see exactly where it happens in a few slides. So a typical, the first thing that people propose as a notion of fairness is often, but not always, statistical parity. So statistical parity says, think about college admissions, for example, or people who are given loans. So that the demographics of the selected group should be the same as the demographics of the underlying population. And that can actually be expressed both of these ways, that the probability that X is in S. If you draw randomly from the people who were given a certain outcome, the probability that you've drawn somebody in S is the same as if you draw from the population as a whole of seeing somebody in S. And it turns out also to be equivalent to that the probability that you're mapped to a given outcome, given that you're in S, is the same as the probability that you're mapped there, given that you're in the complement of S. And a nice thing about this property is that it completely neutralizes these redundant encodings. That you've wiped out the history of whether somebody is in S or not based on when you have this property. But we don't like it for a lot of very specific reasons, and in particular, it permits several of the evils in the catalog. So for example, suppose you have a spa, and you're advertising this spa, and in order to be fair, you have to send the ad to a certain, you have to be equally likely to send the ad to members in S as to members in S complement, but you only send the ad to people in S who are too poor to come to your spa. So you've done something fair-ish, but you certainly didn't do the right thing. So another problem is that it gives you low utility on S when you have low multicultural awareness. So for example, and this was a really strong motivating example through our work. Suppose in the subgroup S, the brightest students are steered to math and the less good, let's say, to finance. And suppose it's the opposite in S complement. Now, if you want to build a quick and dirty classifier for finding bright students, and if the minority, if S is a small minority, you may as well just have a classifier that says, look for people who study finance, because it's right on the majority, and the majority, is a strong majority, so it's pretty good. So not only are you unfair to the bright students in S, but you've also lost utility on this set, and you would have a better utility and more fair classifier if you acknowledged and knew that members of S who study math and science are somehow similar to members of S complement who are studying finance. So you need a multicultural awareness. So this gives rise to what we settled on for our first definition of fairness, which was a notion of individual fairness. That people who are similar with respect to a specific classification task should be treated similarly. So people in S who study math should be treated similarly to people in S complement who study finance. And we called this fairness through awareness because it uses this multicultural awareness. And of course, who is similar to whom changes a lot according to the classification task. Now, what's next? So our work involves a piece of science fiction. It does not exist. It needs a metric that says for the given task how far and how close two individuals are. So we need a metric, a distance notion, on pairs of individuals. Ideally, this would be ground truth, but it's science fiction. On the other hand, okay, so in reality, we'll be working with society's best approximation. Of course, the best approximation can change over time. And there are some examples where you get this. So credit scoring. You've taken people and you've given them a number. That implicitly gives a distance metric on them, their difference in their credit scores. There are various college admissions formulae where you take people and you reduce them to numbers, and again you have differences. I'm going to skip the description of this project, Eileen. Okay. We also advocate having the metric be public and open to discussion, revision, and regulation. And just to see how important that is, there's a wonderful but very sad, difficult reading book by Michelle Alexander called The New Jim Crow, where she points out that in the United States, discrimination in housing and employment, public assistance, and voting is legal. And yet the practices, especially she emphasizes in the US war on drugs, that create the criminal classification are highly racially biased. So it's really important to look at the metric and look at how people are being defined as similar and dissimilar. Now, think about credit scoring. You might say that treating similar people similarly is going to run into problems because suppose that credit scores are sort of smushed uniformly between, I don't know what the lowest is it 300 and 800, right? And suppose, well, that the scores are dense on that line. You may feel, well, you have to draw the line somewhere. And if you draw the line somewhere, you may have two people on opposite sides of the line who are very close to each other and who are experiencing radically different outcomes. Similar people are not being treated similarly if you draw the line somewhere. So what is a computer scientist to do? What do we always do in a situation like this? We randomize. So now, instead of being mapped directly to an outcome, you're mapped to a distribution on outcomes. And what we require is a Lipschitz condition, which says that given the right notion of distance on distribution, so for example, total variation distance, the difference in the distribution that x gets mapped to and that y gets mapped to is bounded by the distance between x and y. And this will ensure that similar people are treated similarly. Now, I mentioned earlier that we had a way of incorporating the vendor's input. So the vendor could specify for different kinds of people or different individuals what is a loss associated from their point of view by mapping an individual x to an outcome O. And when you have that information, you can assemble it into a linear programming. So what it is it's going to minimize the vendor's utility loss subject to the fairness conditions. So it's kind of like our view of privacy in the differential privacy world. You say, this is the definition of privacy, what's the best utility you can get subject to that requirement? Here we're saying, this is the definition of fairness, what's the best utility you can get subject to this criterion? So the loss function provides a bunch of soft constraints, and the fairness conditions are hard constraints. And this is what the linear program looks like. Notice that, so what am I doing here? I'm looking for a collection of mappings that take x to a distribution on outputs, and I want to minimize the expected loss subject to the Lipschitz constraints. Notice that membership in S does not play a role here at all. Membership in S comes into things in defining the metric, but it doesn't come into the linear program. Now, you may wonder, what does that mean for, say, how good or bad this scheme will be for the group? And the answer is, it depends on a quantity known as the earth mover distance between the distribution on people in S versus in S complement. How these two populations differ. And again, there isn't time to go into this in detail, but the bottom line is, if the groups are similar, meaning that they're close in earth mover distance, then individual fairness does yield group fairness. But if the groups are very dissimilar, then that won't be the case. And when you step back and think about it, that is not a surprise. You have two very, very different populations with very different, home circumstances, let's say. They're not going to be equally good students. And if you are sort of ensuring that similar students are treated similarly, you won't expect to find balance in the student population, in the accepted student population. So this approach can actually be modified to give some kind of fair affirmative action. And the general idea is that we're going to map a uniform distribution on the members of S to a uniform distribution on T via a linear programming that is minimizing earth mover distance and satisfies the Lipschitz constraints. Obviously, you can't understand the details of that. I will mention that it doesn't matter, and the roles of S and T could be swapped. But what does it do? It turns out that when you use these conditions, you're going to end up with statistical parity. And when you use the Lipschitz conditions, you get individual fairness. What this whole thing is doing is it's relaxing the similar treated similarly for pairs of people where one is from S and the other is from T. It's making a best possible effort there, but it is doing similarly on S and similarly on T. And okay, so that's what it's doing. It has some antecedents which we were totally unaware of when we were doing this work, but there's beautiful work by John Romer, who is an expert on distributive justice, and he particularly cares about education. And he talks in one of his writings, for example, about stratifying students based on the education level of the mother, and then looking at the distribution within each stratum on how many hours students spend on homework during the week, and treating the top percent similar, treating each percentile similarly across these different strata. And he makes a very moving point that if you have a child in a home where the education level of the mother is low, it may not even occur to the child as something that is done or something that is possible to spend many hours a week on homework. Now, a similar philosophy underlies the University of Texas's policy of guaranteeing that for a UT school, if you are in the top 10% of your high school class, then you're guaranteed admission. So what this says is, you've basically, since the schools are, the schools have done their own segregation, sadly, by education level in part of the family. And what this is guaranteeing is that the best students in each of these different strata are viewed similarly to each other. So this is what our thing would boil down to in that setting. So we have a powerful framework, and it gives us a way of measuring disparity. We can adapt it to yield affirmative action. we could modify the linear program to ensure statistical parity or proportionality if that was essential for whatever the application is. Of course, there's this science fiction component, which is the metric. So future work, the metric, the metric, the metric. I believe that the metric is unavoidable in the following sense, that if you have a system that is actually fair, then it will turn out that optimizing as a vendor with respect to what that system is doing is the same as optimizing with respect to some underlying metric. So if you have something is fair, then somehow magically you've built the metric in. And there's been some progress recently working with a student, Cristina Ilvento. We have some progress on formalizing and proving this conjecture. Of course, treating similar people similarly is not the whole story for many reasons, and many of you in the room can probably start coming up with some, as I speak. But don't. I'm going to spend 5 minutes telling you about a burst of activity from this year alone. So 5 papers in approximately 5 minutes. ProPublica, online journal, had an article about a system called Compass that is made, that was being used for predicting recidivism. And the data are totally available. Anybody can look at them. And what ProPublica did is look at the data and determine that there was an unequal risk of error between African Americans and white Americans. So there was labeled higher risk but didn't reoffend. So false positives were lower in the white population than in the African American population. And false negatives were higher in the white and lower in African Americans. So this seems terribly unfair. And North Point, the creators of Compass, responded and they said, "What are you talking about? Our system is well calibrated in the following sense. Let's say it assigns a risk score of 0.2 to a group of people. Then, they say, and the data bear this out, that 20% of the white people with such scores recidivated and 20% of the black people with such scores recidivated. So they were well calibrated. Apparently in the testing literature, things like this are called test fairness. So Compass is well calibrated. What's going on? Well, there are a couple of papers that show the following. No test fair or well-calibrated prediction that is imperfect, so it makes mistakes sometimes. No imperfect predictor can simultaneously achieve the same false positive rates across demographic groups and false negative rates across demographic groups if the base rate of recidivism is different across these groups. So it's just math, and in fact, the key formula looks like this. This is the false positive rate. So let's look at one particular group. This is the false positive rate. This is the probability for that group of recidivating. This is the positive predictive value. So given that you've been assigned a score of yes, this person is going to recidivate, what is the chance that they actually recidivate? And this is the false negative rate. So if you're test fair, this term is going to be the same across the groups, and you can see that if the p's are different between two different groups, something has to give. Okay, that was 3 papers. The last, another paper by Hart, Price, and Trebro take equal false positive rate and false negative rate as the requirement. They say this is going to be our definition of fairness. And what they say is, here's something you can do in practice that will give you a classifier that satisfies these conditions. First, learn an unfair predictor. Of course, I'm not telling you at all how it's really done. First, you just go ahead and learn your predictor, which is probably unfair, using your best possible machine learning algorithms. And then they're going to apply a certain post-processing step that has appropriate training data derived from the data that were similar data to what you used in the first step. And you're going to modify that predictor that you created at the first step and create one that satisfies these fairness constraints. Okay. So this is very practical because they're actually talking about not tinkering with the original workflow and only adding an extra step. So it's an interesting approach. Okay. But who said that the right thing to do is to take as your definition of fairness equal false positive rates and equal false negative rates, or even equal false positive rates? That's not the tradition in our criminal justice system. So we have Blackstone's quote about better that 10 guilty persons escape, meaning escape punishment, than one innocent one suffer. Benjamin Franklin says this with a ratio of 100. Maimonides uses 1,000 in talking about being put to death. And in Islamic law, there's a maximum erring toward leniency. So we don't know what's the right definition to be using, but again, it's probably going to end up being context sensitive. And the fifth paper by Joseph Kearns, Morgenstern, and Roth, this is Aaron Roth, is they take something like equal false, so they're thinking about a situation where being classified positive is a good thing, like being given a loan or admitted to school. So they're taking something that seems similar to, in spirit, equal false negative rates across different demographic groups as a fairness requirement and studying the so-called bandit setting. And they're proving a gap, which if you know anything about machine learning and bandit reasoning, there's a notion of regret. And what you want to do with your learning algorithms is minimize your regret. And they're showing that if your algorithm is fair, then it takes more time to do the learning. And you experience more cost, which is captured formally in regret. So, last slide. There are a lot of definitional and philosophical issues that remain. And I believe that this is a much, much harder area than privacy-preserving data analysis. It's hard to find any baseline, and even when you have it, I don't know, maybe we'll be lucky, maybe the field will turn out to be easy, but I don't see how. The consequences of leniency, again, think about Burke's point, that the killings are intraracial. Romer's attitude, Romer's philosophy is invest and invest and invest in the education of disadvantaged children. Compensate them, equalize their future opportunities, compensate them for aspects of the environment that are beyond their control. And he's very passionate and speaks very movingly about this. So for example, if they're poor, if their parents are alcoholics, if their parents are uneducated, his view is that you must invest even more in these children so that not only can they have the opportunity to develop themselves fully, but also so that they can contribute and be skilled workers for the society. That he views education as, an equalizer and something that is providing a workforce. I put this up because I don't know what to think about it. So I'm not telling you, follow this, but take a look at the writings of Deborah Hellman. She argues somehow that accuracy and correctness is the wrong lens through which to address wrongfulness and discrimination. So a lot of the writings in my field seem to say, and I'm sure I've done this too, I certainly found it on some slides, although I have since purged it, that when things are correct, they're fair. She says not necessarily, and she gives an example. So her key concern seems to be compounding previous injustice, or at least this is part of it. And she gives us an example. Battered women are discriminated against in insurance because the risk that something is going to happen to them is indeed higher. And for her, this is just completely wrong. Again, it's a philosophical issue. Okay, thank you.
I wonder whether you are aware of related work in the area of data mining, anti-discrimination data mining, where the idea is that one should sanitize the training data sets in order for the inference rules that are being extracted from them are not based on discriminatory attributes either directly or
Right.
indirectly.
Yeah.
Work by Tedeschi and
Tedeschi et al. Right. So in fact, again, it was a short talk, and I couldn't give the whole history. So in 2008, I think, was the first paper by Tedeschi et al. And there's a set of works that tend. You could describe them as saying when people are near the boundary, you should change their labels. And that's a kind of sanitization of the training set, and then what you learn on it is more fair. So so there's that, and there are a few other things that involve regularizing that have a similar spirit to them. Yes, indeed. Thank you for bringing it up. Yes?
I think I'd like to follow up on Giuseppe's remark. There are these two traditions, I would say, roughly speaking, more European tradition of discrimination-aware data mining, and the more US-based or US-originated tradition of differential privacy-based. And I think
This is not based on differential privacy.
yeah, okay. So I take that back. But let's say the more US-based thing. And I was over the summer and the autumn talking very much to the FedML community,
Yes.
which is a community very much rooted in the US
Right.
that's very, let's say, active about going into this area. You cited a couple of authors from them. And we agreed there is just too little interaction. And
the FatML workshop, the next one is next week, in just a couple of days, in Barcelona, part of NIPS.
Some of the papers you mentioned.
So, and in fact, at least 3 of the papers that I mentioned, this was a banner year, at least 3, you're absolutely right, I'm so glad you brought it up. At least 3 of the papers that I mentioned are there. And I do all encourage, I encourage people to go. Yes.
right. No, but I think what would be your impression of how we could do better in appreciating the work of the respective other community? And like you were mentioning this thing about instances at the boundary, so I think, of course, you have to give a short answer here, but then you're zooming in on one particular aspect, whereas there's a lot of different work in discrimination-aware data mining. There is, for example, a lot of work, a very good paper on situation testing methodology, which pretty much corresponds to this search for the elusive, and it remains an elusive metric, but that builds on social science practice that is well established and has a long legal history. These colleagues, Cordelia et al., showed that you can actually apply situation testing in order to address also automated decision making. And it seems to me there is a very different vocabulary that the two communities are using, and that there seems to be a big communication problem in the middle. What would you recommend we do so that everybody listens more to the respective other community?
So that's a great question, because in this particular case, I was not aware of all of the things that you mentioned. I was aware of some of them, but not all of them. The FatML website has a collection of papers, references, resources. And what I will do, what I do for this, is I read. And I have to see what the other people are saying. And I think that's what everybody should do. And if those resources that you mentioned are not listed at the FatML website, tell the owners and get them there. Because until we can actually know what the other people are saying, we're stuck. But there's sort of no substitute for actually doing your homework.
I'm afraid I'm under very strict instructions to finish it before class. So I do see the two last questions by the gentleman. After the panel discussion, we will have drinks. I'm afraid we'll have to continue questions at drinks. So let's thank Cynthia again and let Christy